What if an icicle grew underwater and froze everything it touched? This is a brinicle, an underwater icicle nicknamed the ice finger of death. Born from sea ice physics in the deep cold, it reaches down like a glass blade and turns living water solid. Stay with me. We'll rewind to where it begins, and why this fragile killer is also a window into the engine of our oceans. At the surface of Antarctica and the Arctic, sea ice formation begins. But when seawater freezes, it refuses the salt. Salt rejection. That salt is squeezed out into tiny veins, brine channels, turning the trapped fluid into hypersaline brine, extra salty, extra dense, and far colder than the water around it. Supercooled and heavy, the brine finds an exit and drains downward through the ice like a liquid blade. Where it touches the ocean, it chills the surrounding seawater below its freezing point in an instant. Ice blooms around the falling stream, building a fragile tube, the brinicle, encasing the flow as it grows. Underwater icicle, yes. But it's not frozen still. It's a conduit, a siphon of cold chemistry. In the right conditions, calm water, steady brine supply, and just the right geometry, the tube lengthens by centimeters per minute, sculpted by gravity and temperature. The physics is simple and ruthless. More salt means lower freezing point and higher density. The brine sinks, the ocean skin freezes, and a hollow icicle follows the path of cold. When the brine stream reaches bottom, it spills and crawls downhill. Still hypersaline, still sub-zero. Where it flows, it flash freezes life that can't move fast enough. Starfish, urchins, worms. It's a slow-motion avalanche you can outrun, if you can move. You've seen the Brinicle time-lapse. A white finger touches down, and a sheet of ice races outward, trapping anything in its path. Myth versus reality. The ice finger of death sounds apocalyptic, but it's local and short-lived. Divers aren't stalked, and fish usually slip away. The danger is real for small, slow invertebrates pinned to the seabed. In the lab, dyed brine demonstrates the effect. Hypersaline plumes descend, water freezes on contact, and a brittle ice sleeve forms around the flow. It's the same physics, scaled down. Salt, temperature, density. Every creak and crack is a negotiation between heat leaving the water and salt concentrating the brine. Too turbulent, and the brinicle fails. Too warm, and it never starts. When everything aligns, the ocean rides with cold. Brinicles are small, but they whisper about something vast. Density and temperature driving motion. The same principles behind Earth's thermohaline circulation. As polar waters cool and concentrate salt, they sink, helping power the global conveyor that moves heat, nutrients, and oxygen around the planet. A brinicle is not steering the currents. It's a tiny, visible signature of sea ice physics, the kind of microprocess that hints at the macro engine. Life responds with quiet brilliance. Polar fish and invertebrates deploy antifreeze proteins that latch onto growing ice, blocking crystals from spreading. Microbial mats ride the edges of brine channels, making a living wherever gradients exist. Salt, temperature, light. In Antarctica and the Arctic, survival is mathematics with heartbeats. Lose heat too fast, freeze. Tune your chemistry just right, endure. The brinicle reveals a lesson. Even the cold writes ecology. And adaptation is the footnote that refuses to vanish. Tides shift. The brine starves. The brinicle stills, then splinters, and the ocean exhales. In the silent dark, an icicle writes with cold. Then lets go. The deep remembers. And we keep learning, one frozen fingerprint at a time.